Assembly at Karolinska Institute has today decided to award the Nobel Prize in Physiology or Medicine 2012 jointly to John B. Gurdon and Shinya Yamanaka for the discovery that mature cells can be reprogrammed to become pluripotent. I would like to ask Professor Thomas Perlman.
This year's Nobel Prize awards a discovery that has changed the way we understand how cells in the body become specialized. And it has provided entirely new tools for effective development of drugs and new therapies. On this first picture, we see a fertilized egg that develops first into an embryo and then into an adult human with all its specialized cells such as muscles, nerves, and skin. As we all know, this process always moves in the same direction, from immature cells in the embryo to specialized cells in the adult. A common metaphor for this process visualizes how cells move downhill in a landscape to finally reach their destinations as specialized mature cells at the bottom of deep valleys. Scientists believed for a long time that our genes are likely altered in this process in ways so that this journey could never be set in reverse. And it seemed impossible for mature cells to travel back all the way to the immature state at the top of the mountain. Now, John Gurdon changed this view by a groundbreaking experiment in frog cells. He thought that if genes, contrary to the common view, were intact in mature cells, its nucleus should be able to develop when moved into the cellular context of an egg. So he destroyed the nucleus of an egg and used a fine pipette to transfer and replace it with the nucleus from a mature intestinal cell from a tadpole. In most cases, this modified egg could not develop. But in a few cases, it developed into normal swimming tadpoles and later adult frogs. At first, many were skeptical and surprised about this result. But this paradigm-shifting discovery was confirmed. And we now know that the same experiment works to clone mammals, the first being Dolly the sheep, but later also mice, cows, pigs, and other animals. Gurdon had shown that the nucleus of a mature cell retains all genetic information that is required to generate an animal. But could this also be done in intact cells without dissecting out the cell nucleus and using a pipette like Gurdon did and placing it in an egg? Shinya Yamanaka, over 40 years later, made the discovery that also whole intact mature cells can be reprogrammed, and that this could be achieved by a surprisingly simple procedure. Now, Yamanaka, he studied genes that are important for the function of pluripotent stem cells. Pluripotent stem cells are found in the early embryo and can develop into all different types of mature cells in the body. And he thought that some stem cell genes may induce pluripotency if they would be transferred into mature cells in a mouse. 24 candidate stem cell genes were selected. His target cell was a skin cell from a mouse. Now, usually scientists transfer genes into other cells one by one, but in a strikingly bold experiment, all of these 24 genes were introduced in one single step into the skin cells. And a few cells became reprogrammed into cells that could generate all the mature cells in a mouse. They had now become pluripotent. Further experiments demonstrated that only 4 genes were needed for this induction of pluripotency. He named these cells induced pluripotent stem cells, or iPS cells. The iPS cell technique is a truly groundbreaking discovery that has opened up a whole new research area in cell biology and medicine. For example, iPS cells can now be generated from patients with disease. And from these iPS cells, mature cells can be cultured so that we now have a procedure that gives access to new cell models for disorders that previously have been very difficult to study. This is a final picture that summarizes the fundamental discovery made by this year's laureates and illustrates how John Gurdon and Shinya Yamanaka reinstated pluripotency by either nuclear transfer in 1962 or by gene transfer in 2006. Thanks to these two scientists, we now know that development is not strictly a one-way street. Here finally we have the two laureates. To the left, John Gurdon from Great Britain, who is a professor at the University of Cambridge and the Gurdon Institute. To the right, Shinya Yamanaka, born in Japan and a professor at Kyoto University. Thank you.
Good afternoon. Thank you very much, Francis, for the invitation and for the kind introduction. I really appreciate induced pluripotent stem cells. Cells, we may be able to treat those many patients suffering from various diseases and injuries by cell transplantation therapy, human embryos. So from Jamie Thompson's work, I learned that human ES cells could be very useful, but at the same time, they try to make ES-like stem cells, not from human embryos, but from somatic cells, like into somatic cells, we may be able to induce pluripotency. Based on this hypothesis, we should be able to do with these patient-specific iPS cells. We could use these cells in toxicology, making disease models, drug screening. A good example of such applications in vitro, those iPS cells, and we can make beating cardiac myocytes. And then we can adult fibroblasts, which may be equivalent to mouse tail tip fibroblast, although we don't have tails. So Kazu evaluated quality of human iPS cells, students and fellows in my laboratory. This is my laboratory in Kyoto. I have like 40 people, including some strange, weird student like this guy. This is a boy student. And also I have a small lab in San Francisco. It's small, but we all have very good people in San Francisco. With this, I'd like to finish my talk, and thank you very much for your kind attention. Thank you very much again.